Donc on va démarrer la session avec la présentation donnée par Alessandro. So Alessandro will talk about some of the results from the project SAFE, and he will do his talk in English. Please. I don't know which one you prefer, this mic? Or?
I saw that. I'll stick here actually, that's probably better.
Okay, please go ahead.
Okay, so hi everyone. I'll be presenting two SAFE projects on trained networks against adversarial examples. The underlying techniques are network over-approximations, as you'll see. Let me start with some... Sorry, is that okay, like that? Okay. Yeah, I'll switch perhaps, that's better. The underlying techniques are over-approximations, I've said, but let me start with some brief introduction. So let's say we have a neural network that's trained for images. It correctly classifies this panda image, as you may expect, but as you perhaps most of you know, turns out that if you perturb even slightly this panda image, you get yet another image of a panda, but one that's quite dramatically misclassified as a type of monkey. So what's going on here is that there is a set of imperceptible perturbations to the image. We have an adversary in the loop who's able to pick one of these. And once feeding this to the network, it can prove that the point goes the wrong way of the classification hyperplane, meaning the image is misclassified. Of course, we don't want this to happen, especially in a safety critical context, so there's a lot of work on trying to prevent this. Theoretically, the idea is that you take your favorite loss function, let's say you're doing cross entropy for classification, and you're replacing it with the worst case around the input pole. So for each point in the data set, you get the worst case of the allowed attacks. The problem is that this worst case loss, it's pretty hard to compute as it entails taking this set of allowed attacks and feeding the whole set to the network and getting an output set. Once we have this set, we need to compute the worst case loss over any point of the set. And yeah, turns out it's NP complete even in the simplest cases. Why is it the case? Well, it amounts to computing globally a non-convex optimization problem. So we have a bunch of constraints, the set of allowed attacks on the inputs, let's say. All of the layers of the networks also come up as constraints. Let's say we have affine layers, linear layers, convolutional, whatever. We have nonlinear activation functions such as ReLU. Checking whether computing that worst case loss entails solving this problem exactly. So we can already do this at training time. There's a bunch of ways to get around this sort of limitation, and as you may guess, the idea is approximating it. One way is through lower bounds to the worst case loss, and this is by far the most popular approach. It's called adversarial training. The idea is that you get your favorite adversary, you plug it in the loop, and you replace each of the training points with the adversary computed by your heuristic. You then check the loss on that adversary and try to train a network that correctly classifies against these adversaries. You get something like this, which does its job with respect to the adversary in the loop, but it may still misclassify parts of the output set, as in the example. Indeed, if you train like this, you're not currently able to provide certificates that the network is robust. So you have no formal guarantees of robustness against stronger types of attacks. The other way around is to use upper bounds to the worst case loss. This is called certified training. In order to do this, the idea is relatively simple. So you replace that output reachable set with an over-approximation. Once you have this over-approximation, you can compute the worst case loss over the over-approximation itself and train a network that correctly classifies the whole orange set. It's going to look like something like this. How do you compute the over-approximations? It turns out that you're kind of stuck with fairly loose over-approximations because you have differentiability problems otherwise. And so the most popular approach is called IBP, interval bound propagation, which replaces the ReLUs with, I don't know if I can point, okay, with this sort of hyperrectangles that are, again, a fairly loose convex relaxation of the set. So as a result, if you're set on solving this pretty hard task, you're going to get a network that doesn't really classify the original images very well. So there's a pretty large cost in standard performance. So what this work is about, at least the first of them that I present, is overcoming this sort of limitations of training through over-approximations. The starting approach is a paper from ETH from 2 years ago, and they have a pretty simple idea, which is instead of computing the over-approximation over the entirety of the input set, they propose to instead do this over a subset that's, as long as the subset contains an empirical attack, they argue that this is good enough. And then they plan to deploy harder, like better verifiers post-training. You can basically try and solve that non-convex optimization problem post-training. And they prove that they can achieve pretty good results in terms of trade-offs between accuracy and robustness. We start, in the first contribution, we start from this sort of idea and ask ourselves whether there's something more general. So we define a notion of loss expressivity, which basically means the ability to span a continuous range of trade-offs between the lower and the upper bounds to the worst-case loss. It turns out that, more formally, this means that this L of alpha loss must be between the two bounds for alpha in 0, 1. It must be continuous and monotonically increasing for, the parameter in those values, and the extrema must be met. The definition is fairly simple, and indeed we show that you can actually implement this through convex combinations, and you can take these convex combinations between lower and upper bounds, so just to recall, between adversarial points and interval over approximations. Within the loss function, we call this CCIBP, so this would be within cross entropy, let's say, between loss functions, and this has a multitask learning interpretation. Or you can even do this in a log space, getting this sort of product of losses. What we argue here is that it doesn't really matter the way you implement this definition, but what kind of buys you performance in the area is just the ability of meeting expressivity. So in order to show this, we train networks on Cypher 10 with the 3 different schemes. And there's 3 plots that are qualitatively identical. That's indeed exactly the point. So let's just focus on one of them. Let's say the middle one. What I'm plotting here is for increasing alpha values. So the more we go towards over-approximations, we have quite interesting behavior. First of all, the standard accuracy of the network is gradually going down. So as you go towards over-approximations, you are decreasing your ability to correctly classify the points. At the same time, verifiability through the same over-approximations employed at training time is gradually going up. But more interestingly is what happens somewhere in between. So this is the tightest approximation we can get to that non-convex problem, and this is a good estimate of the true robustness of the network. So you can see that it first goes up for increasing alpha values, but then it goes down along with the standard accuracy, implying that basically anything above this alpha threshold is basically wasting the network capacity into learning something that's provably robust through cheap schemes. So the whole goal here is to be able to train the loss function so that we are in this intermediate regime. Indeed, if we do this on larger scale data sets, say from the ImageNet family, we can show that each of the 3 losses has pretty good results with respect to what was previously in the literature in terms of both how many points they're still able to correctly classify and for how many points you can get a robustness certificate. So indeed, this proves that if you want to get provable robustness, expressivity is effectively all you need in a way. Nevertheless, if you have some degree of familiarity with these data sets, you'll quite immediately spot that the absolute performance is quite depressing. On ImageNet, actually, we can get around 90% nowadays, implying that the trade-offs between provable robustness and standard accuracy are still, to be improved upon, let's say. Okay, so that brings me to the follow-up work, where we basically try and consider less conservative notions of robustness. So the idea is that, as many people in the community argue, like robustness to concrete adversarial attacks as opposed to certificates is enough for many practical use cases. In order to get that, you train through the attacks themselves, as I said before, but the problem is that if you want to do this well enough, you need strong attacks and you get, say, an order of magnitude more training overhead. Some people have, therefore, sought to decrease training costs by training with cheap attacks. So roughly speaking, these are attacks that just take a single iterate and they typically land on corners of the allowed attack space. The problem, though, is that if you train a network to correctly classify against these points, you're going to get something like this, which kind of neglects most of the output set. Indeed, as it was shown a few years ago by CMU people, there's a very dramatic failure case, even the name itself is quite dramatic, I would say, called catastrophic overfitting. The idea is that along the training, you're overfitting to the weak attack, so you can see that the error to the weak attack is going to 0, so we're doing great. But at the same time, the error against a stronger adversary in the loop goes to 100%. So we have virtually no robustness to stronger attacking schemes. This is, of course, a problem, and so some people from Oxford, for instance, have tried to mitigate this by the addition of noise in a training loop, or by enforcing, and this is a work from EPFL, by enforcing local linearity on top of the loss. We start from these works and ask ourselves whether over-approximations can be useful for the same type of purpose. Indeed, we try and measure a notion of the over-approximation size over different adversarial training schemes. So this is like the cheap one-step attack, this is a 5-step attack, and a 10-step attack. So of course, like the overhead goes accordingly. But we can see that the over-approximation size with stronger attacking methods is greatly decreasing with respect to the failing methods. So the idea basically is, what if we were to use the same sort of loss function from the iClear paper to achieve the same effect? Instead of tuning it around here, so to get high verifiability, we want to tune it around here, so basically closer to the lower bounds, to the worst case loss. Before actually showing the results for this, so this is a team in our paper appearing this year, let me just comment on the training overhead. So PGD10 and PGD5, so the stronger adversarial training schemes, are quite expensive with respect to a one-step attack, but using one of the expressive losses is slightly cheaper than PGD5. So we kind of try and further reduce the training overhead by coming up with a very cheap proxy for the over-approximation size. Turns out that this can be computed by just doing a forward pass over the network with the weights in absolute term. So you remove the bias and you get the absolute value of the weights, and you just add this as a regularizer on top of the loss. Turns out that, as I said, this acts as a very good proxy for the over-approximation size, and it behaves very, very similarly to the expressive losses that explicitly use the over-approximations at training time. Okay, to kind of cut it short, turns out that if you use any of these schemes, you can actually prevent this failure case. So this is, the red line is the attack going against corners, basically. Turns out that while you're training for this, at some point, as I was also mentioning before, robustness dropped to 0 throughout training. And this is not the case if you add proxies for the over-approximations or the over-approximation themselves within the training loss. On top, if you use a fancier method, let's say the Oxford paper adding noise, it still fails for stronger attacks, so on larger perturbation sizes. We can show that by adding the over-approximation in the loop, we can actually avoid, even for here, and we can match the performance of PGD5 in most cases. Roughly speaking, in the paper, we try to explore when this pays off even more, and somewhat intuitively, it's just when you can compute tighter over-approximations. Indeed, if you have a shallower network, so before we're showing a pre-activation ResNet 18 results, this is just a 7-layer CNN, you can see that the gap between the methods is even smaller, and we can actually almost match the performance of PGD10 just with like a small overhead on a single-step attack. If we train for longer, things get even better as we can compensate for the problems that over-approximation support at training time, and just using the over-approximations alone can actually outperform multi-step attacks. So this is fairly interesting. Okay, so wrapping up, I presented a series of like training schemes that employ over-approximations to achieve provable adversarial robustness. Turns out that if you want to maximize performance in this space, you need to kind of smartly combine this with actual attacks. And these sort of schemes are still useful against more empirical notions for robustness. But, you know, as I've said, a lot of work still needs to go into improving the trade-offs themselves. Thanks.
Thank you, Alessandro. We have questions in the audience. Yes.
How does thank you for the presentation. How does your method compare with approach that use Lipschitz constraint to have certified robustness structurally?
Thanks for the question. So yeah, actually this was, I mean, I kind of glossed over this, but the state-of-the-art of training with Lipschitz constraints is called SortNet. And it's this baseline effectively. So you can see that it achieves like strictly worse trade-offs between robustness and accuracy. And this is mostly due to the fact that, you know, like the architecture here is using a sorting operator as activation function, which creates a bunch of different problems in the training process. And so at the end of the day, it's pretty hard to train networks that have low Lipschitz. At least so far, we're not quite good at that. And so just empirically, these sort of methods based on over-approximations of standard architectures seem to be outperforming them quite consistently.
Okay, thank you. But some architecture like LIRESNet, for instance, something like that, I think.
So those architectures are conceived for L2 norm. So actually, this is a big difference, right? So what we're doing here is we're considering L-infinity examples, and all of the like L2 Lipschitz architectures would not really have a good L-infinity constant, and so they just don't perform very well. And it turns out that like theoretically L-infinity seems to be a harder problem as far as Lipschitz is concerned, and this is by far the best performing L-infinity Lipschitz method so far.
Okay, perfect. Thank you.
Thanks.
Okay, is there another question? Okay, so if not, let's thank Alessandro again. So we'll now move on to the second presentation, which will be given by a different Alessandro. And he'll be talking some of the results from causality.
So hello everyone, I present here the work. It was done conjoint work with Audrey. So this is the line structure causal model, some using deep generative model. It was joint work done with Audrey Poisson. That's work finished her thesis now. Nicolas Chenot, Michel Sebag, and Marc Chanoin. And this is the third presentation in relation to the project causality. When you talk about related causality, most of the time you are interested in establishing the relationship between the cause and effect. And because if you analyze what decision make some decision, they are not only interested in what will be the prediction, but you need to say, okay, what will be the outcome if I take some actions? And say, if I change the system, what will be the outcome? And this that means that in the end, causal inference will be related to ask what if question. That means counterfactual question in the context of this work. For instance, just a question if we want to answer such type of question, we need a causal model. And this causal model needs to relate to describe the relationship, the causal structure, the relationship between the variables. I also need to have the causal mechanism that will drive the outcome between the variable. For instance, if I want to intervene, for instance, in the interest rates, I want to say, okay, what will be the outcome if I change my interest rate in the relation to the inflation, for instance? Okay? So, in the context of the causal inference, the causal framework, we start by causal questions. For this, you assume that you have knowledge, you have observation data, in this case, and domain knowledge. And for the data, to make the assumption simple, you assume that you know all the variables, or at least you know I need to explain how the relationship between the variable, their model, use the causal link. So we start by this assumption that I have the data and the knowledge. After, sometimes you don't know exactly what will be the relationship, the underlying causal structure. You need to learn a causal graph that describes the relationship between the variable. And once you have identified the causal graph, now you need to try to identify what will be the cause and the effect that between the variable. Once you have that, you ask the question, okay, does my query is identifiable? That means that is a unique model. If not, what are the assumptions that I need to make this model identifiable? And then be able to answer the causal question. Okay? Just a quick review here, because in the course of this course, on this work, you have different type of question. For most of them, you have what's called here the pure causal hierarchy or the causal ladder. Where in the first layer, you have the data, you have the observation, where most of the time, as explained yesterday, you have the machine learning rely on. My outcome will be related to what I have observed. But now, when you move for the second layer, you call here the L2 layer, you say, now I want to make some action. What will be the outcome if I take some action? And what will be the next one said, okay, imagine that now I imagine a world, in a counterfactual world, where what would happen if I have not taken the action or if I had taken different action. Okay, I take the action A, but what would happen if I have not taken action B, for instance, okay? And what is the challenge here is that only use data for underlying layer to answer a higher question, the higher layer. Only the data is indeterminate, cannot do that. You need more further assumption. What we are interested in, what about the assumption that I need to do, that I need to make, to answer counterfactual questions. Okay? And for this, you need to have a model. For us, the model be what is called structural causal model. You can assume, to be simple, is a DAG, where the DAGs, the nodes represent the variables, the relationship between the links, the edge, represent direct cause effect between the variables, and for each node, for each variable, there is a causal mechanism, and the causal mechanism describes what are the function between the relationship between the variable. And for each variable, you have the noise, or the unknowns. Okay? In this case, for each variable, you said that the function, the causal mechanism, will be related to in the function of the parts. For instance, say, okay, what the smoke cursor, what the effect of smoking in the line cursor. Say, okay, in the intermediate by tar and by C. But if I just said, if I check here the definition of FT, functional mechanism, I know that I have FT will be defined function of only DT, the part, what's called the part, and the noise of the function. Okay? So this is the model that you learn to learn. For us, most work assume that the F is the causal mechanism is linear. In this case, let's say, no, let's assume that's not linear. How can I approximate the F? Over the year, I have observed many neural networks, doing the characteristics of neural networks, try to approximate this type of function using neural network, and for that we call deep structure causal model. That means that use neural network to represent the function. Why deep structure causal model? Because as the property of the neural network, there is only few assumptions related to the functional form of the causal mechanism, and also because we are focused on the, I want to emphasize the distribution of the causal intervention when I work exactly in the counterfactual operation. As we rely on neural networks, there are many different questions, because as I start to answer more of this, stabilize the deep structure causal model as with a network, there is some problem related to explainability, related to the black box, and I have a variability of neural networks. What are the guarantees that I have that you can be able to answer my counterfactual question? Okay? And the application that is also used for different fairness and algorithms, that is very important. So, if I want to understand what is exactly the question here that I want to try to investigate, it is, okay, doing that I have on observational data, I want to answer question for the top layer, that is counterfactual. And for this, I imagine that I have a world of structural causal model, where I have an M star here. This is the true structural causal model. There is this total M star, that this model can answer any type of question for the layer, for the N1, L2, observation, intervention, and counterfactual. However, this model, you don't have this model is not available. So let me see, what will be the constraints that I need to assume that I have, that I need to reduce this class of, a subclass of structural causal model, which, with this constraint, now, I try to approximate to have my M star hat. However, as M star hat is also not possible that I'm using a model that approximates the reality, this M hat here will be how far is my M hat from my really true causal model, the structural causal model. And once I have this structural causal model, that my M hat I will model using neural networks, if I have it correct, how far it is, I will be able also to answer all these, all the causal queries. Okay? So related to this, I have a very rich literature today. Most of them focus on the machine learning aspect, machine learning components. Okay? And what we have observed through this work, there was a lack of, there is no work nowadays. There was comparing how are the guarantees that I have, consider I have a heterogeneous neural networks, architecture, what are the hypotheses that I need to make to use different architecture, and what was the performance of each of the works. Okay? So we investigate this work for two different viewpoints. One of them was for the research viewpoint was, okay, assume that I know the structural causal graph, I know the structure, the data, based on observational data, what's called here my G star graph. What will be the capabilities of deep generative model, DGM here in our case, to answer counterfactual question? In counterfactual question, that means that for us is I need to approximate, that means what we will call the abduction step, you need to approximate the value or the distribution of the noise, the U. Okay? And for the practitioner point of view, was okay, imagine that I have now a bunch of causal model that is different work try to answer different type of questions. How can I choose the most appropriate one that I have? Consider I have my base of my application, okay, or my some interest, and what are the limitations of each of these works? Okay? First, we start to consider for what are the characteristics of these existing methods, they call here deep generative models, to approximate the abduction step. That means approximate what are the value or distribution of the noise. And for that, you can classify in three they can be classified in three classes. One of them we call unversable explicit. In this case, they are all the methods that assume that the mechanism is inversible. I can invertible it. Where the mechanism is invertible, it can be very easy, very directly to me compute the abduction step because it's just the inverse of the mechanism. Okay, and for this there are different. So that means that I'll be able to answer counterfactual question. There is another class that more try to enlarge the inverse mechanism. Okay, and now will be also considered all the methods, the functions, all the mechanisms they are not invertible. In this case, we lose the characteristics to directly compute the abduction step. Instead, now you need to approximate. That means that now normally most of the work, they use an autoencoder to learn the noise. And in the first case for investment, they normally rely on condition normalizing flow. And the second one, amortized explicit, they are able to compute the abduction step, but now only use autoencoders. Okay? And amortized implicit, they say, okay, instead of trying to learn autoencoder, let's use adversarial networks to encode the noise. And for this case, you need to rely on sample rejection. And in the mechanism here, you just bear the conditional implicit likelihood of the loss. Okay? And there are different types of methods. So in the last one, the second, you can lose the direction, but you approximate. The third one, so instead of learn, you try only to use sample rejection, and there is no guarantee that you will be able to answer all type of counterfactual, the noise, abduction step directly. Okay? So consider how they work. Say now you can class the structural causal model, the model that you want to answer counterfactual, related to the type of noise or the architecture that I use, the capability of the architecture that I use to model my causal mechanism. The more general one will be the SM, that's how they work, they use a deep conditional generative model. There is no theoretical guarantee in this case. Or more history, I have NCM, that's be how they works, where the causal mechanism, they rely on FNN, fish-fowl neural networks. And there is some guarantee in this case. You can express you can use NSCM to answer L3 specific. That means that once I know the true causal graph, I'll be able to approximate it. And we rely on this to say, okay, I have some guarantee related to identifiability of the counterfactual question. And the BGM will be the class of all the methods that assume that the noise is bijective. Okay, the mechanisms are bijective. And the guarantee, they say, okay, I can do some, I can provide some guarantee related to answer counterfactual questions, the more challenging one. When I'm decoding the Markovian, that means that X directly cause of Y. And I have an instrumental variable, that means I'm between the variable of interest and the outcome, I'm intermediate by another variable, and the confound is only between all these variables. That means that there is a common cause between the variables. Oh, sorry. My outcome, or if I'm the case of the backdoor criteria. These are the guarantee that the class of SM, the guarantee that provide also rely on BGM. And BGM, as I said before, it is explicit. They also allow us to compute the abduction step, the automatic abduction step. So if I want to summarize here, you can observe that first consider to the SM, you have the DFCM that how they work the deep conditional networks to modelize, but there is no guarantee. But if I need to have some guarantee, I can use NSCM, that in this case will be any network that's implemented by FNN. That is the guarantee that F3 will be identifiable. If I'm F3 quantified identifiability, I also have L2 identifiable also. For the true SM, consider that we know is also true in the SM. If it is not, there is a technique that you can use, near ID, that you can prove that it will be able to only know more or less what is the position of the common confound and be able to answer the question. It will be identifiable also. And DGM that said, okay, I can be the noise once it's bijective, I can compute the abduction step automatically, and also have some guarantee related to consider that I'm in three cases, the Markovian and instrumental variable, mediator, and the backdoor criteria. Okay. So this is related for the relation for, okay, once I have all of the class, the taxonomy of the work that I have, one question they highlight say, okay, down there I have this bunch of methods. For each of the class, I have different methods that implemented, follow the same architecture or different architecture. How can I choose one of these methods? How can I pick one to choose? And what, based on the characteristics of the problem that I have. Okay. For first of them, you start to observe, okay, let's analyze the work that you have today, consider what will be the hypothesis and guarantee of each of this work. And for that, we analyze, okay, what would be the hypothesis that the work required related to the structural causal model, the model you are doing, the class of DGM, that means is was explicit or implicit, related to how to compute the abduction step. The causal study, do I need to know the true causal graph or not? Though the method is able to handle hidden confound, that means variable that I don't know, the unknowns, okay? What the assumption relates to the data assumptions, and what are the additional guarantees that we have. Related to the structural causal model, so I'll explain, most of them will be NCM, rely on feature networks. That means I have some guarantee, I cannot compute automatic reduction step, but I have some guarantee related to L3, use sample rejection in this case. And related to the class, the structure, most of the work assume that we know the underlying causal graph is a very strong assumption, but other words say, okay, instead of assume that you know the true causal graph, it is sufficient to know only the causal order to model the work. And for hidden confound, only 5 of the approach can handle hidden confound, that means variable that what was observed and the common cause between two variables. And in this case here, we use most of the one recommendation to use NCM, because NCM said, okay, once I don't know exactly what it will be, the exact position what will be the hidden confound, but if I have some guess related to where it is, there is some guarantee that you can to be able to identify robust hidden confound, identify the hidden confound. When you assume that the graph is semi-Markovian. Okay. Another assumption related to the data, except for the works that work with image, the architecture that only work with the image, most of them there is no constraint related to the data. Some do some assumption that the data are related to the sample and the number of variables, high dimension. But in general, there is no constraint related to the data. Okay. For the abduction step, as I said before, if my approach is inversible, that means that DGM, BGM, NCM, all of them do compute automatic, BGM automatic, NCM by some rejection, but otherwise not able to do. When I'm not able to do, I need to use another work, need to plug another approach to be able to approximate the abduction step. For instance, okay, you use for instance, the decaf, you can do one of them, you use NeoID to try to manually implement it. Okay. And related to the additional guarantee, there is some more that say, okay, I assume that once if I don't know exactly, I don't have guarantee related to compute the adoption step, but once I assume that my noise is inversible, that means I can compute it and it will be sufficient to do it. And finally, there is one say, okay, if I use NeoID, there is, instead of have identifiability, try to move to point identifiability, in this case, to have the guarantee that you'll be able to answer the counterfactual question. Once you say, okay, once we analyze what was the guarantees and the hypothesis that we was able to use different type of work, one of them would say, let's analyze now how was this work, what they evaluate, and what type of the application that I use this work. And what you observe is that there are high heterogeneity, there is no standard, no benchmark today that establish how to test the different type of different models, different works. And we consider to the data set, to what the layer that we can answer the question, what are the type, how they compare between each of the works, and what type of application that we use. This was the criteria that we used to compare the works. So you can observe for the data sets, there are high heterogeneity because due to the heterogeneity of the causal ladder, okay, for each of the question that I want to use. Some of them relate to the B-learn, that was, once I assume that I have the causal graph, the DAGs. I try to now approximate the causal mechanism by know the Bayesian networks. Okay? So the data set, most of them here will be adults, the celeb, they use for the image, or FMR, FMNIS for also for the image. Related for the page, for the how only 5 words can really do with the L3, that's mean counterfactual. Most of them rely on the intervention, that means I can only answer a question that once I take some action, but I cannot imagine what would be the word where I take a different action. Okay? And then for the comparison, most of the works, they only compare if we use synthetic data or use other approach. There is no comparison between the method, except for instance, in this case here, for Vaca and Calef, they compare between the approach, the work, they compare between them, Vaca in this case, DCM. So that means that the works today they compare, but there is no one nowadays that say, okay, let's compare what are the performance, use the same data set to the same assumption. And for the application, they are also very, different type of claims, relation for most of them, for the domain of fairness, try to answer counterfactual questions, what is fairness or not, try to predict what would be the outcome if, for instance, Alice was male, okay? And other for the domain, there is also for the explainability. I need to know what would be the difference. How can I find someone that's near to the point that I want to different outcome? And related for the robustness for the machine learning point of view. And some work rely on in domain and out of domain that augmentation to try to in this case to generate the data to answer counterfactual question. Okay. For the sensibility of the application, so that means that most of the sensibility will be related to healthcare, that in this case will be the in domain of the fairness or explainability. Okay. So related for what you can summarize for this work is that, okay, what was the learning action that okay, related to evaluation, there is no standard benchmark to decide to compare, to really properly compare how they works. No work, there is no work today consider, okay, what are they efficient, because they have a heterogeneous architecture, related to the efficient, how much number of samples I need to have the data, computing time, some robustness to the selection bias, or, as I explained before, as most of the works assume that the true causal graph, you know the true causal graph, this is a very strong assumption. What you need to do is say, okay, now maybe I don't, what has happened if my causal graph is incorrect, or if I only have some partial knowledge about the causal graph. I don't know exactly the true causal graph. You have seen that if I know the partial order is sufficient, but even the partial order can be correct, but there is no one analyze this type of work today. And related to how to do the absorption step, compare different architectures, that is BGT or NCM, there is no comparison. That means that related to the SCM, what we focus today, what we're doing today, say, okay, let's generate different structural causal model and try to see what will be the performance of this method once my M hat is very far or close to my true causal graph, structural causal graph. Okay. And related for the point of the partial identification, identifiability, there is no, as I said, out the work assume the causal graph exists, and there is no hidden confound, as I explained before. For the hidden confound, what we have observed is that if you execute another approach that connect what's called narrow IG, you'll be able to do, but no one have done this today. We need to do it and see you'll be really able to identify the hidden confounders. Okay. Related for the practical point of view, what this work shows that, okay, the causal graph needs to be validated by expert. Nowadays, there is no work that assume that the causal graph is true, and once I have the question, answer the question, I don't know exactly if this is really answer the true question, this is enough. Okay? And related to the sensitivity analysis, need to observe, okay, what will be the impact of the hidden confound, observe variable in this case, or if I have some selection bias. Another point is also observed there is no one consider what the uncertainty that I have. We need to quantify the uncertainty of the answer of the causal. And I answer, provide my causal answer, but not provide some uncertainty, not quantify the uncertainty relation to it, and some how to measure the error. Okay. And finally, what you are considered said, okay, what I need to consider is more. Need to use this type of method. I can use this type of method to generate data that are more close to real data. Say, okay, once I have pick one day correct method for this work, this is a good opportunity to use more real world application, more close to data. That means I have a causal data generation mechanism. Okay? So that and this case can be used to benchmark different type of method, or can be used as causal data augmentation. Okay, so thank you.
Thank you, Alessandro. Questions? Maybe I can start off with one. So maybe I missed the detail in terms of the size of the data sets that we're looking at. Do you see any particular limitations that you might?
There are some that I have today related to the data is that there is not only some meta, some there is image, but then no one today say, okay, what the minimum data sum that I need to have? There is no work today. There is no assumption today. But whereas there is no one compare, real benchmark compare, let's analyze what is the real performance of the different type of methods that have studied, what are the minimum points or the bound. There is no work today, there is no assumption today. And you have not observed. This is what I want to, because there is what type of the question, what type of guarantee do we need? And for that, there is no one, I haven't observed any constraint related to the data sample, the number of points.
Okay.
That is for related to the dimension. Some methods assume there is only work in high dimension, but not in low dimension.
Great, thank you. So if there's no more question, we can move on to the next talk and thank Alessandro first. So now we'll have a presentation by Panayotis, who will talk about some of the results from his project Foundry.
Okay, let's see. It seems to work. All right. Wow, it's blinding. Okay, so first of all, it has been said enough. Many thanks to the organization team and the directors for the PEPR for bringing us all together. It's a lot of work, so thank you, and for putting everything together. As Karteek said, I represent the Foundry project, which is about the foundations of robustness and reliability in AI. And I am in the POLARIS team in Grenoble. And what I want to, what we've been working on for some time now, let's see, no? Okay, all right. So what I want to talk about is has to do with basically the reliability of the training methods that we're using to essentially train all our systems and to basically understand a bit better what they actually behave like and what type of guarantees we can really have. And the method that is the most common one is SGD, stochastic gradient descent. And so what I want to talk about is some recent results that we have. Whoops, sorry, I'll get the hang of it. About, first of all, the long-run distribution of the iterates of gradient descent, where it converges, where it spends most time, which points are most likely to arise, etc., etc. And also, much more recently, some bounds, actually some pretty sharp estimates about the global convergence time of stochastic gradient descent. And There was supposed to be another QR code here for the second paper, but someone messed up the times, and so it's going to appear on tomorrow's archive posting. Anyway, so because I have to say that there is a lot of technical machinery involved in actually even stating some of the results, I'm going to start with a no-frills, very basic version of the results and some pretty easy examples. And then I'm going to start progressively get more technical towards the end of the talk, and at some point we'll have to break for lunch, so I will stop there. Now, what we really want to study here is, again, as I said, the behavior of SGD, stochastic gradient descent, in landscapes, non-convex landscapes like the one that we encounter in the training of deep neural nets, which of course can be very, very, very anomalous. They have a lot of local minimizers, spurious local minimizers. Then they have a lot of crevices, cliffs. There's a lot of randomness involved. So as you can tell, it is a pretty difficult problem. And what we do want to find, ideally, is well, the global minimum of this function. This is what we ideally want to get. Of course, this is a super hard problem that we always essentially relax. But what makes it even harder is that, again, for typical applications, we only have access to F to the objectives through stochastic gradients, so just the real gradient plus some noise. And we are running SGD on it, trying to find, again, a minimum of this function. Okay, now, as I said, because this is a very hard problem, but also a very important problem, it has been studied a lot in the literature, and there's a lot that is already known for this, but typically revolving around the following results. First of all, you say, okay, I cannot deal with a non-convex case, I will deal with a convex case, then you know a lot of things. You have near optimal convergence rates. You can refine them. There was yesterday there was a talk about how you can accelerate the convergence under some interpolation assumption, etc., etc. We really know a lot of stuff about the convex case. Sadly, what we know about the convex case means absolutely nothing about the non-convex case. In the non-convex case, the only thing that we kind of have is that if we run stochastic gradient descent and we do some random stopping scheme, at least this is what the theory says. In practice, no one does that. In practice, one always runs SGD and looks at the last iterate. But anyway, the guarantee is that if you're doing some random stopping scheme, then after T iteration, you will get a gradient whose norm, whose actual real norm is of the order of 1 over square root of T. So these are near criticality guarantees. All right, and then because these are near criticality guarantees that cannot even tell you whether you are near a minimizer or even a maximizer or a saddle point or whatever else, there is also a literature which has to do with whether SGD avoids saddle points in the sense that it escapes them, or in general is not found with high probability near saddle points. All right, now. All this is pretty classical, but it doesn't answer the real question that we would like to answer, at least from a global optimization perspective. And these are, okay, so from all the points, all the critical points that SGD visits, which are the most likely to be observed, and by how much? So this has to do with the distribution of the iterates of SGD over time. And then, second, if we do want to find, let's say, the global minimum of the function to be optimized, or even more generally, let's say, some class of specific minimizers which for any reasons we believe may have sharper generalization bounds or whatever, how much time would we need to wait in order to actually get there? All right, so these are some questions that we do not know the answer to, and these are also the questions that I'm going to try to provide at least some partial answers to. All right, and so I'm going to start with with very basic examples. So I'm going to sweep all assumptions for the objective function under the rug. We're still going to be working with non-convex landscapes like that, and we want to minimize them. And we'll take a very, very simple case where SGD is just gradient descent with Brownian noise. Is this a realistic assumption in the context of neural nets? Not particularly, but at least it gives a very concrete, a very nice and easy to state result well, easier to state result in this case. All right, and as I said, in this general context, what we want to find is, first of all, what is the long-run distribution of iterates? So given a set, how much time does SGD spend near this set? Okay, in the limit, when we look at the long-run distribution, this is what is known as the invariant measure of, this would be an invariant measure of SGD, and also the time that it takes for SGD to reach the vicinity of a global minimum. All right, so these are the two quantities that we would like to study: the empirical distribution, or the occupancy measure of SGD, and the global convergence time, the time it takes to get within delta, let's say, of an optimizer. So here is where I will try to show a first video, trying not to break the machine. Okay, and this is just to show you how SGD really behaves. You can see that very quickly all the iterates of the SGD, all these particles, go to the vicinity of some of the critical points of the function that I showed you, and then while there, they stay there for a lot of time. Actually, you can show that they spend there an exponential amount of time, but eventually, as you can see, they transit from one point to another. All right, now these transitions actually take up a very, very small amount of time relatively to how much time they actually spend near the minimizer, near any minimizer, but you see that they happen all over time. Okay, they never actually stop. So this is actually something important to keep in mind, that SGD, especially with SGD with a constant step size, never actually converges. It actually concentrates and keeps moving. Any given SGD particle will keep moving around space, spending most time around different local minimizers. And what we want to study is exactly how much time does it spend near any specific minimizer. All right, so I'm going here, and I'm going there, okay. The result, again, I'm giving you the easier version of the result with Gaussian noise, is that if you take any critical point of your function, and you look at the at how much weight does SGD end up putting on this point, meaning how much time does it spend on this point, then you will end up showing that. Then you can show, it is not easy, but you can show that this is actually it actually follows what is known as a Boltzmann-Gibbs distribution. Which is the distribution well known in physics, describing semi-classical gases with given energy levels. And because semi-classical gases, there is a temperature parameter. This temperature parameter, in the case of SGD, is exactly the step size of the process. All right. So that's the basic result that you need to keep in mind for the distribution. I will show you the full result later. But what it tells you is that in the Gaussian regime, the probability that SGD stays at a neighborhood of the probability that you observe SGD at a neighborhood of a given point of a given minimizer is exponentially proportional to the value of this minimizer. All right. Now, how about the time that it takes to reach the global minimum? I will try, again, another video. So, okay, so what am I showing here? Again, this is a cloud of SGD particles, and I'm also plotting their tail, meaning that I'm plotting a piece of the trajectory going back in time for a few iterations. What I'm doing is that once this function, all the particles start here, and the global minimum is here, so I'm going to stop the process once I get very, very close to that point. In that case, that particle will disappear. So what you should expect to see is this cloud slowly disappearing and becoming a dot over here as I'm taking out particles once they reach the global minimum. All right, so here's what happens. You will see that after some time, there is still a lot of mass in this spurious local minimum over here. What has happened is that even though the process actually started in the middle, because this is what happened, a lot of particles actually moved over here to this to this local minimum. They were trapped there for a lot of time, and this is why you saw a lot of particles here moving before ultimately doing this path that they should have taken from the beginning in order to reach the global minimum. And as you can tell, it is because this has a high probability of happening, and the time that you're going to be trapped here can be quite big. This type of transition is what actually ends up dominating the heating time, the global convergence time of SGD. And indeed, the actual result that you can show for this case is that if you take this transition into account, well, what do you have to, and again, these transitions are exactly what correspond to starting at the minimum here, instead of going directly to the global minimum, moving over here, because you were unlucky, getting trapped here for a lot of time before moving back and then back to the global minimum. This heating time, this global convergence time of SGD ends up being exponential in what? In the barrier, the difference in potential between this critical barrier and the lowest critical point, the lowest minimum other than the global one that you have here. Why? Because this barrier, P2 minus P5, is the largest barrier that you may have to overcome on the way to the global minimum. And what we show is that actually the expectation of the mean global convergence time of SGD is precisely exponential in this value, in this gap, in this maximal gap, again divided by eta sigma square. So eta being the step size and sigma being the variance of the noise. All right, how much time do I have? 10 minutes, okay. All right, so these are all the very basic results that I showed you. The applicability of these results relies on two basic assumptions. First of all, the results are only for SGD, and also the function that I showed you is actually quite simple, because the structure of its local minima is, well, pretty simple. It has a sort of a one-dimensional structure. You have like a chain of minimizers, saddle points, maximizers, saddle points, minimizers. Okay, so in this regard, it is a fairly simple case. Now, the good thing is that if you compare what you get in theory with the observed heating times of SGD, the fit is actually pretty strong. All right, so what I'm showing here are precisely the convergence time in log scales for different values of the step size. And you see, you run a lot of you perform a lot of runs of SGD, you do some statistics, you compute the mean convergence time, and you see that the theory fit, which is precisely what you get from this expression, follows the observation pretty well. All right, but again, this has to do with two facts: that the function has a relatively simple structure, and the noise is Gaussian, which is like the most well-behaved noise for our case. In general, this is not what we have, so we need to get our hands dirty in order to get more general results. All right, so here is where the technical part starts, and well, I'm just going to state the blanket assumptions that we have for the analysis. We always consider a non-convex function f, and the assumptions that I'm talking about here is Lipschitz smoothness. So this is basically C2 with bounded growth, and we want the function to be coercive and non-coercive, so we would not want the function to have plateaus at infinity, because if it has plateaus at infinity, then the iterates of SGD can actually escape to infinity, so this is not something which is of interest anyway. And also we need some regularity for the critical set, so basically we do not want very pathological functions like, you know, what topologists like topological sine curves, Cantor Devil functions and things like that, all right. So these are the basic assumptions for the objective. For SGD, so here what we want is the assumptions that govern the noise that is entering the process. Here, well, what we want is, we want actually to be studying SGD, not GD, so we want to have noise with positive covariance. We want this noise to be bounded, to have bounded growth, and we want some tail control. Hence the sub-Gaussianity assumption here. Now you can relax a lot of these assumptions. I don't want to show the most general version of the results that you can get. This is already more than enough for what we want to do. All right, and basically that's that. What do we study? As I said, for the distribution of the iterations of SGD, we want to study the mean occupancy measure of the process, which is how much time it spends on average on a given set. All right, and we want to look at the limit of this occupancy measure in the long run. Okay, this is what is known as the invariant, as I said, the invariant measure of SGD. And, well, the thing is that now, to study it, when we do not have this Gaussian noise assumption and we don't have a simple structure for f, well, there could be some parts of the space where the noise is very low, so SGD might be spending significantly more time there, etc., etc. So in order to study this question, you now need to go into much more depth regarding the statistics of the noise. Now, the gradient noise, the way that you study any process is it is captured by, for instance, the moment generating function, or here it is more comfortable to look at the logarithm of the moment generating function for the gradient oracle. This is what is known as large deviation theory as the Hamiltonian. And also the corresponding Lagrangian, which is the convex conjugate of this Hamiltonian. All right. Based on this function, you can construct what is known as a large deviation principle, which tell you how that if you have a process which is sampled on the same point, well, then you can have a very good handle on how on what is the limiting probability to observe it in a certain set. The problem here is that we're not talking about a single point, but about an entire trajectory. So you need to get your hands even dirtier and construct what is known in physics and large deviation theory as an action principle, which is basically the integral over curves of this Lagrangian. All right, And the reason that this is important is because there is a variational principle at play which tells you that the most likely curves that you are going to observe under SGD are precisely those that minimize this action functional. All right. So there's a lot going under the hood here, which I'm not going to explain. But the key question that we want to answer is how probable, I mean, with these tools, if we can estimate how probable it is to observe a transition from one critical region to another. All right. And this is where the action comes in, because it allows us to define rather the cost, a specific cost function between different points, and in turn between different critical points or critical components of f. And this is what in turn allows us to take all the critical points of the function and put it on a graph, on a directed graph, where the vertices are the various critical points of f, the edges are, you know, just paths between them, and the weights are given by precisely these large deviation costs, these transition costs. All right. For the Himmelblau function that I showed you before, this is what the corresponding transition graph looks like. I mean, at least graphically, there are of course weights here which I'm not putting. But then the important thing is that thanks to this graph, you can construct the energy, you can define the energy of any given critical point. And what is this energy? Long story short, it is basically the minimum cost you have to pay to get to this point from any other critical region of the function. All right. These energy levels incorporate all the statistics of the noise and the global geometry of the function f, and in the end, what you can show, at least informally, is the following result: that first of all, the critical points of f is visited exponentially more often than any other point. Okay, so that this is at least good. We know that the time that SGD spends away from critical points is exponentially small. You can also show that critical components are, well, visited according to this Boltzmann-Gibbs distribution that I showed you before, but not with respect to the function value, but with respect to these energy levels, all right? And what this tells you in particular is that minimizing components are visited in turn exponentially more often than non-minimizing ones. So you have also what I was talking about in the beginning, an avoidance result, meaning that the time that SGD spends near non-minimizing points is exponentially small. And finally, that the ground state of the problem, meaning the one with the lowest energy, is visited exponentially more often than any other critical component. Now, this is the formal version of what I said. The key is this Boltzmann-Gibbs distribution that I mentioned before. All right, and but what I want to keep you in mind, want you to keep in mind is that even though you can relate these energy levels to the function levels or to the function values of your objective when the noise is very Gaussian-like, if it isn't, and you have a different distribution of the noise in different region of space, then this can be completely different, and the ground state of the problem can be very different than the actual global minimum of the function, which means that SGD will actually end up spending more time in non-global minimizing regions. All right, and this has to do a lot with some of the deep versus shallow minima phenomena that we observe in the training of neural nets. All right, good, great. I only have one slide. So that's for the distribution of SGD, for the iterates of SGD. The last thing I want to talk about is what happens for the time, for the convergence time, but I cannot resist the temptation of showing you exactly how this looks like. And so what I'm showing you here is basically SGD particles. These are 1, 2, 3, 4. These are the critical points of the local minima of the function. And this, the wireframe, is the theoretically computed invariant measure, and it will start filling up based on the empirical distribution. All right, and what you end up getting is something which looks like that. Over time, things clear up. Everything concentrates around the global minima, and in the end, it restarted, but in the end, you have a picture which is like that, which shows the agreement between the empirical and the theoretically computed invariant measure. All right. So, last thing, one more thing. Control L. What about the heating time? All right. So here, the heating time, the global convergence time, this should write, sorry, that's a mistake. It should read the global convergence time, not the long run distribution. But in order to measure the heating time, what you need to do is you need to take the energy of your global minimizer, which is your target, but not only that. You need to also adjust it by a certain term which we call a pruning, and which looks at this transition graph that I showed you before and takes out different global different local minimizers. And what this pruning term tells you is that you look at the pruning that actually has the minimal that actually leads to a minimal cost of getting to your target set when the point that you prune does not exist. All right. So you take these two quantities, the non-pruned energy and the pruned energy, you take the difference, and this is exactly what ends up controlling the convergence time to SGD. Now, this is a very non-trivial result to even read, but at least in simple cases like the 3-hump camel function that I showed you before, it allows you to get a very explicit handle of what controls and which barriers control the global convergence time of SGD, which again agrees very well with what we observe in practice. So I guess that's that. I think I'll stop here, and thank you.
Thank you, Panayotis. So we have time for maybe one quick question. Yes.
Thank you for the talk. Maybe a clarification on the second part of the presentation. It seems to me that the property you evidence on your model of noisy gradient descent is actually very similar to what you obtain with simulated annealing. So is it by chance, or Gibbs sampling, I mean, or simulated annealing? Is it by chance, or can you indeed relate the two models?
Well, I would say I would be careful with this comparison, because yes, there is an exponential, yes, there is a Gibbs-like law, but the exponents that you get, for instance, in simulated annealing, which are simply the function values, and what you get here are completely different. So I would say that the similarity between simulated annealing and the end result that you get here is this exponential distribution, and no more.
Okay. Yeah. Okay. Thank you. Any other question? Yes.
Hello. Maybe a naive question. So you introduced your assumptions you have over your noise. I guess it was slide 25. And I was just wondering if, in which cases, the specific case of noise induced by sampling gradients in the sum of gradients will fit in these assumptions.
Oh, so for instance, if you take any neural net with, let's say, with hinge regularization and whatever, let's say sigmoid activations, no problem.
Okay.
So empirical risk minimization problems, again, with sigmoid activations, or even smooth ReLU activations and some hinge regularization, you have it.
Okay. So it depends on the property of the activations and.
Yes,
Okay.
I mean if you have activations that are non-smooth, so for ReLU per se, this doesn't work. For smooth ReLU, there is no problem, or sigmoid or what have you.
Okay.
Yeah.
Thank you.
Thank you again, Panayotis. Let's
thank you.
the speaker. Okay, so we're going to end this session with the presentation of a tool by Alban, who will present one of the tools from SAFE.
Thank you. So yeah, it should be a short talk, so only 10 minutes, don't be surprised when I'm done. So I'm presenting CaBRNet, which is a library that we are developing within CEA-List. How do I... Okay, not this way. Yeah. Okay, so CaBRNet is developed for image recognition, and so I guess it's important I start to explain what we're trying to do. So there is this bunch of algorithm for image recognition that is meant to be self-interpretable. So by design, they should be able to explain their decision, their classifications. It was introduced by this paper called This Looks Like That, which introduced the ProtoPNet algorithm. And the idea is that you've got this test image, so here it's on the top right. You send it through a neural network, and it gives you a latent representation. So you get these feature vectors. And you compare them, these vectors, with vectors you've already selected during training time. And then you base this, the classification on the similarity between these vectors and the vectors you've already identified at training. So you end up with decisions that are sort of interpretable, because you're able to say, I think this is a Herman girl because the head looks very much like the head of a girl that I had in my training set, and it's very dissimilar from, I don't know, a pigeon or a parrot. But obviously the network doesn't know what a head is or anything. It's all done at training time, and it doesn't really need labels except for the class of each image. And so it's supposed to be interpretable because it comes with some sort of explanation. This looks like that. So this has been quite popular. There's been 20, maybe more extension to this approach. But the problem is the researchers who've been working on this have developed their own repositories. They've written their own algorithms. They use their own training sets. So they're more or less similar, but they are different enough that it's impossible to actually compare fairly the different approaches. And sometimes they don't publish their models. So it's really difficult to compare and to get fair comparison and to do research work. So that's why we decided to develop this platform. It's based on, it's using Python and PyTorch. It's funny because it looked better on my computer. So there are missing, there's missing text at the bottom. I wouldn't be happy, but fortunately it appears on the next slides, so that's good. So we wanted to have it modular, and this is what a model would look typically in CaBRNet. So on the left of this picture, you've got a YAML file that describes the model. It's impossible to read, obviously, but it just gives you a gist of it. So, for instance, we indicate here that we want to have a protonet, so there has to be a Python file that explains exactly how a prototree works. It explains what kind of neural network is used to generate the feature vectors. Here we have an add-on. What kind of classifier is used? So it's a proto-tree. The decision at the end is a fuzzy binary tree. And one of the good things about this is that it clearly exposes the hyperparameters, and so it's very easy, for instance, to compare different variants of the same algorithm, the same architecture. So, for instance, here we have a depth of 9 for this proto-tree, and you can just copy-paste this file, modify the depth to 10, and start looking how different your model is and how more accurate it is, for instance. Second part is compatibility. So we want to be able to support existing approaches. So we've implemented some of them, and the rest is left for the other authors of algorithms. So some of the more popular are proto-PNet, proto-tree, proto-pool. And in order to faithfully represent the existing algorithm, we've also implemented some kind of buggy pieces of code. So just to give an example, proto-PNet was computing distances in a way that ended up leading to negative distances. And in some cases, because we apply a log afterwards, it would completely break the training. So since then, PyTorch introduced a new operator that computes the distances. But so you can still use or run the original proto-PNet, for instance. So that's about compatibility, and there is. So reproducibility as well. It was very important for us to be able to reproduce the results done by other researchers. So there's been a lot of work on dealing with the random seeds, being able to save intermediate versions of the model, and publishing models. So we've worked a lot on that, but unfortunately, it's not always possible to reproduce 100% results. So we've identified problem with, say, hardware, for instance. So if we run the same model on my CPU and my GPU, we will get different outcomes. And some of these differences are really, really big. We get 5% accuracy drop depending on which hardware you're using to evaluate, and 5% is very big. Like, it's what makes the difference between being published in A-star conference and having some kind of rubbish model. And we've noticed that even the size of the batch can influence the evaluation. So it makes sense that during training, the size of the batch is important, because after each batch, you update your model, so obviously it will have an effect. But here, on the same hardware, with the same model, everything identical except the size of the batch, then you get different evaluation, different accuracy. So it's quite frightening, actually. So we did the best we could, but there are some things that we have no control over. The best we can do is actually log the type of hardware that has been used for training, but we cannot do much better than that. And so what do we want to do with this tool? So the goal of this tool is to be able to quickly develop, well, so first of all, to use existing models, but quickly develop new models. And for instance, we had an Italian researcher who worked with us for 3 months, and after day 2, he was already able to start building his model. But we want to do more, and some of the things we want to do, for instance, is look at the quality of the prototype. So I don't remember if I mentioned it. The prototypes are these feature vectors that have been identified at training time. And so on this picture, we see on top this bluebird, and according to the model that is being used here, the head of the bird is very similar to the head of the crow, I guess, on the right. And well, maybe it is actually. Maybe the model is capturing the beak, or maybe not. But so what we want to do is to be able to get a better understanding of what it means that these two things are similar. And so some of the things that we are proposing, we are working on at the moment, is really identify what part of the image is supposed to be similar to the one on the right, and start perturbating the image and trying to capture what it is that has been seen. So for instance, if we see a drop in similarity when we change the color or the shape of the object, then maybe we'll be able to say, oh, okay, this is what has been captured. So there was this assumption, or there is this assumption in this type of approaches that it's sufficient to say that, or it will be obvious to a human that these things are similar, but we're trying to actually understand why they're similar, maybe to be able to reject those prototypes that are actually similar to nothing else. But so more importantly, what we're hoping to achieve is we want to have under the same umbrella a bunch of tools that can be reused for every implementation, right? So Proto-PNet has been developed by some people, Proto-Tree as well, and if you develop something for Proto-PNet to understand the prototype, to get some interesting statistics, whatever, they cannot be transferred easily to Proto-Tree and to all other approaches. Now, having everything under the same umbrella means that we're going to be able to reuse the tools that have been developed by some team and reuse them to other approaches when they are similar enough. And here they're going to be very similar because all of these approaches are using prototypes. And so the future, so now that we've got this platform we want to use to develop our own model, own architectures, because we've got plenty of ideas. We're hoping that it's going to be used by the community and that other researchers will start to use this when they find that there is a real benefit to it. We want to develop metrics that allow us to understand beyond accuracy what makes a model very interesting, and so the interpretability, for instance, and some applications such as the medical, which was what the Italian researcher I mentioned before was working on. And there is extension to time series, for instance, so beyond images. Thank you.
Thank you, Alban. Are there any questions? We can take one or two. Okay.
Thanks for the presentation. So first about your findings about reproducibility issues. So this is something that we all share probably in the room. I think this is important to say, and I think we should have a place. So there are journals now dedicated to reproducibility, but the fact that we get very, very different results when we just reproduce results from a paper just because we change a little bit the machine or whatever is a real problem, I think, in our field. So I think this should be shared a lot more. So thank you for doing it today, but yes. And the second remark is, so this is useful, but for me, I'm working in explainable AI. What is more useful, so I have to remember how Proto-PNet works, but it's a self-explainable system, so it's really dependent on the classifier. So it's not a plug-in thing. I think PROPERTY.NET, if I remember well, I'm not sure anymore. Actually.
No, it's a complete system.
Yeah, so it's very specific, and if I want to use, for example, explanation by examples, I'm not going to use this particular model. I want to use this one, but maybe something else. And I want to compare all of them, and I don't know if this thing that you developed could be integrated in something much bigger, a library for explainable AI that would include any other types of explanations. I think that would be maybe more useful for at least me.
So you mean beyond image explanation?
No, I mean beyond a prototype explanation or prototype-based explanations.
Yeah, that's an interesting thought. Thank you, Elisa. I'm just worried that you know, the more general you get, the more abstract you are, or things like that. So, and I'm not sure how much you actually benefit. So we've made a Python a package of this, so it can be downloaded. So, yeah, well, clearly I don't have an answer to this question, but we can discuss it a bit more.
It sounds like a discussion for lunch, which will be right just after. But thank you again to Alban.
Thank you.